we're going to look at sampling distributions. The reason why sampling distributions are important is because when we take a sample is not always representative of the entire population. In addition, samples are not always going to be normally distributed. So it becomes very difficult to use any of our normal distribution properties with a sample, since it might not be normally distributed. The way that we deal with that is we take sampling distributions. And a sampling distribution essentially is a distribution of all of the possible samples. So we take all of the possible samples that there are, and we find the mean or the standard deviation for every single one of the different samples, and then we find a distribution of all of those items. For example, if 124 students are taking Introduction to College Math at Burbank High School this year, how many ways could those students have been selected to fill 4 classes? Assume that each class has an equal number of students. Well, then there are 124 choose 31, or 1.834 times 10 to the 29th ways that we could select 31 students for 4 classes from those 124 students. Selecting students for a class is like taking a sample of 31 from a population of 124. So when we use sampling and statistics, we're not selecting individuals, but a collection of individuals or a collection of samples. Each sample is unique and has numerical characteristics that are associated with it, like its mean. One can think of sampling as selecting a mean instead of an individual. As you can see from our example, the number of samples possible, even with a relatively small population, is quite large. So to give us a better idea about sampling distributions and their properties, we're going to do some very simple examples. We're going to use the following population data and create a sampling distribution of sample means for n is equal to 2. Draw dot plots of the original population and its sampling distribution. So 4 friends share a 2-bedroom apartment in downtown LA, and each one has only 1 pet. Narek has a dog, John has 2 cats, and Jose has 2 snakes, and Anthony has 3 tomato frogs. If we randomly select samples of size 2 with replacement, meaning that we could choose Narek or any of the others twice, find the mean number of pets for each sample. First, find the population mean and the standard deviation. Second, find the mean of the sample means and its standard deviation. So, this X here is our population. And we need to find the mean of our population. So the mean of our population, we add those things together, 1, 2, 2, and 3, and divide by the total, which is 4. So our mean ends up being 2. The standard deviation. We could use a calculator to find the standard deviation. When we do that, we end up with 0.707. Now, we want the mean of all of the sample means. So that's what this represents. The mean of all of the sample means. And this is going to be the standard deviation of all of the sample means. So in our little table over here, what we are going to do is we are going to find the mean for each sample. So this first sample is we have Narek who has a dog and Narek who has a dog. So we want to find what the mean is of that sample. The sample is 1 and 1. So 1 plus 1 is 2, divided by 2 gives us a mean of 1. Then I'm going to find the mean of a sample of 1 and 2 pets. So 2 plus 1 is 3. 3 divided by 2 is 1.5. And then again, 2 plus 1 is 3. Divided by 2 is 1.5, and so on. So all I did was find the mean of all of these different possible samples. And then I'm going to find the mean of all of those. So the mean of all of these, I'm going to add them all up. 1, 1.5, 1.5, 2. So this ends up giving us 6, 14, 22, 33, and we're going to divide by a total of 16. So 32 divided by 16 ends up giving us 2. We could also find the standard deviation. If I use a calculator and find the standard deviation, I get 0.5 as my standard deviation. So if you notice, the mean of our population is equivalent to the mean of all of the sample means. But the standard deviation is not equivalent. For our population, our dot plot would look like we have one person who has 1 pet. There are 2 people that have 2 pets, and 1 person who has 3 pets. For our sample means, there was 1 at 1.0, 4 at 1.5, 4 at 2.0, there was 6 for 2.0. And there's 4 for 2.5 and 1 for 3. And this is the sample means. So if you notice, the shape of the distribution for both our population and our sample means is bell-shaped or normally distributed. So with this population, we would have the ability to use our normal distribution and the concept of the normal distribution and be able to find proportions and percentages. However, that is not always going to be the case. If we repeat the work in example 1, but Jose gets another snake and Anthony gets another tomato frog, our population changes to 1, 2, 3, and 4. And the mean of that 10 divided by 4 is 2.5. The standard deviation is 1.12. And then again, I'm going to take samples. So a sample of 1 and 1 has a mean of 1. 1 and 2 has a mean of 1.5. 1 and 3 has a mean of 2. And 1 and 4 has a mean of 2.5. 2 and 1 is 1.5. 2, 2.5, and 3. 2, 2.5, 3, and 3.5, and then 2.5, 3, 3.5, and 4. If we were to add up all of those means and divide by 16, we would find the mean of all of the sample means, which is 2.5. And then if we used a calculator, we could find the standard deviation. The standard deviation is 0.79. So if you notice the mean again, the means are equal, but the standard deviations are not. If we were to create our dot plot, here we have for our population, every number of pets, there's only one person for each. This is our population. But for our sample means, a mean of 1, there's 1. A mean of 1.5, there are 2 of them. A mean of 2, there are 3 of them. A mean of 2.5, there are 4 of them. A mean of 3, there's 3 of them. A mean of 3.5, there's 2. And a mean of 4, there's 1. So in this case, even though our population is not normally distributed, our sample means are normally distributed. And this allows us to then use those normal distribution properties for any type of population, whether or not it is normally distributed or not.